This chip costs more than a house. It draws more power than 50 homes. And right now, there aren't enough of them on Earth to satisfy demand. Not because we can't design them fast enough, but because we're running into the actual laws of physics. Welcome to the most expensive arms race in industrial history. And almost nobody outside Silicon Valley understands what's actually being fought over. For 20 years, the chip industry's problem was making transistors smaller. That problem is basically solved. TSMC can etch features a few atoms wide. The new problem is thermodynamic. You can pack tens of billions of transistors onto a chip, but you can't get the heat out, and you can't get enough electricity in. The newest Nvidia GPU package draws up to 2,300 watts from a chip smaller than your palm. Multiply that by tens of thousands of chips per data center, and you're not building a server room anymore. You're building a power plant with a keyboard. Nvidia didn't just build a faster chip, it built a full computing platform. Blackwell, the current generation, fused two massive dies into one package using a technique called chip-on-wafer-on-substrate. Its successor, Rubin, goes further. Multiple compute tiles and dedicated I/O dies working as one unit, paired with next-generation HBM 4 memory delivering over 20 terabytes per second of bandwidth. Nvidia says Rubin's flagship GPU hits 50 petaflops of AI inference compute, more than double Blackwell. And every major cloud provider, from Amazon to Microsoft to Google, is already lined up to deploy it in the second half of this year. That's the strange part. Nvidia's biggest customers are also racing to replace it. Here's the part most explainers skip. It doesn't matter how good Nvidia's design is if it can't be built. Every leading-edge AI chip, Rubin, Google's TPUs, Amazon's Trainium, Microsoft's Maia, is fabricated on TSMC's 3-nanometer process in Taiwan. And that process is running at essentially full capacity, with demand outstripping supply by a wide margin. Then there's advanced packaging, the process of fusing compute dies to memory stacks, which is its own separate bottleneck. And the memory itself, HBM, is made by only 3 companies on Earth: SK Hynix, Samsung, and Micron. One island, one packaging technique, 3 memory suppliers. That is the actual choke point of the entire AI industry. So the hyperscalers stopped waiting. Google is now on its 7th generation of custom TPU silicon, codenamed Ironwood, purpose-built for AI inference, arranged in pods of over 9,000 chips linked by a proprietary optical network. Anthropic runs more than 1 million of these Ironwood chips for Claude, the first time a custom AI chip has hit 7-figure deployment at a single customer. Amazon has Trainium 3, its first 3-nanometer chip, built specifically to train and serve models for partners like Anthropic and OpenAI. Microsoft has Maia, purpose-built for Azure and Copilot workloads. Meta has its own MTIA line. None of these companies makes chips for fun. They make them because renting Nvidia's compute at Nvidia's margins, at Nvidia's scarcity, was starting to look like a strategic vulnerability, not a convenience. Analysts now project Nvidia's share of the inference market, not training, inference, the day-to-day running of AI, could fall sharply by the end of the decade as this custom silicon scales. But there's a fundamentally different approach quietly maturing in research labs: neuromorphic computing. Instead of brute-forcing matrix math the way GPUs do, chips like Intel's Loihi and IBM's NorthPole mimic how actual neurons fire, sparsely, only when there's new information, using a fraction of the energy. IBM states NorthPole achieves roughly 20 times the energy efficiency of a top-tier GPU on certain vision tasks. The catch? These chips can't run a modern large language model. The software ecosystem, the programming model, is decades behind CUDA, and today's neuromorphic hardware tops out at a few 100 million parameters, not hundreds of billions. This isn't going to replace Rubin or Ironwood in a data center. But for drones, satellites, and edge robotics, anywhere that battery life matters more than raw throughput, it may be the quiet second front of this entire war. Which is why every one of these companies is also playing a geopolitical game. The chips powering this entire race are fabricated almost exclusively on one island, 90 miles off the coast of a country that claims it. Export controls, tariffs, and diplomatic maneuvering now shape chip roadmaps as much as engineering does. When a government changes a licensing rule, it can freeze a $100 billion product line overnight. The AI chip race isn't just Silicon Valley versus itself anymore. It's semiconductors as a matter of national security. Every generation of this hardware, Blackwell, Rubin, Ironwood, NorthPole, represents a different bet on how intelligence gets built at scale. Some bet on raw power, some bet on vertical integration, some bet on mimicking biology itself. None of them have won yet. And the outcome of this race will quietly decide who controls the infrastructure the next decade of technology runs on. If you want the deep dive on how TSMC actually became the most important company on Earth, that's next. Subscribe, and I'll see you there.